This chapter will cover the basics of simulating pneumatic forces in Kangaroo. To be clear, we won't be simulating the effects of air pressure on meshes, but rather mimic the inflation of meshes using the pressure goal in Kangaroo. The following example is a simple definition of taking an icosahedron and inflating it like a balloon. You may open the Grasshopper file provided in the resource folder to follow along. Bring Weaverbird's mesh icosahedron component into the canvas. Subdivide each of the 12 faces using Weaverbird's split triangle subdivision. Set the level of subdivision to 6. This is our base mesh for the inflation exercise. Before we proceed further, let's first understand how the simulation works. Pressure goal can be understood as a variation of load goal, wherein each vertex of the mesh experiences a force vector in the normal direction. To visualize this force, deconstruct the mesh, and use the vector display component. These arrows depict the direction of the force vector, and depend on the shape of the mesh. Another important consideration is the direction of mesh normals, which can be reversed using mesh flip function. The next step is goal assignment. Begin by setting up the basic goals like show, edge length, anchor goal. Show goal is to preview the mesh, and edge length is to assign spring properties to edges. Connect the mesh to show and edge length goals. Set the length factor to 0.1, or any value between 0 and 1. Anchor goal is required to hold the mesh in place during simulation. Deconstruct the low poly icosahedron, and assign the vertices as anchor points. The last goal is pressure. Bring it into the canvas. Pressure goal requires the input mesh, which is this subdivided icosahedron, and strength value that determines the amount of inflation. For this input, always start with a numeric slider ranging between -1.000 and +1.000. Set the slider 0.1, and connect to the strength input. Merge all goals, and connect with Bouncy Solver. Reset, and enable the solver. Use list item to isolate the first item from the output list, which should be the simulated mesh. At first, the icosahedron mesh collapses into a 12-pointed star shape, because the edge length function is stronger than the pressure force. Start increasing the pressure strength slowly, and notice the mesh starts inflating. Keep increasing the value, and at some point, the mesh bulges out of control and explodes. This is why we start with a very small value for pressure strength, and increase it slowly. If we start with a numeric value beyond this threshold, the mesh geometry will explode without appearing on the screen. To restore the mesh, reduce the pressure strength value, and reset the solver. We may also assign a negative value for pressure strength. A negative value reverses the force vector, working in the opposite direction to the positive pressure strength. Try to recreate this definition with different starting mesh, like mesh plane, mesh cube, and mesh relaxation output from Chapter 8. In the next chapter, we will combine all the mesh goals learned so far to create a recursive pneumatic geometry.